James Webb finally looked into Alpha Centauri, and what it stunned the scientific world introduction. In August 2025, humanity pointed its most advanced eye in history at the nearest sun-like star in the sky and found a planet. The James Webb Space Telescope locked its infrared gaze onto Alpha Centauri A, and in the processed data that came back, a faint but unmistakable point of warmth appeared. A gas giant, roughly the mass of Saturn, orbiting just over 4 light-years away. The nearest star system to our own had a world. For a few extraordinary weeks, this felt like one of the defining moments in the history of human exploration. Not just a scientific milestone, but a fundamental shift in how we understood our cosmic neighborhood. Alpha Centauri had always been the closest star. Now it was, possibly, the closest solar system. Then, 2 months later, the planet was gone. A second independent team pointed Webb at the same star in October 2025, using the same instruments, the same techniques, the same configuration. They expected to see what the first team had seen. Instead, they saw nothing. The point of light that had read as a Saturn-mass planet in August had vanished, leaving no trace, no residual glow, no debris, no explanation. What followed was one of the most fascinating and unresolved episodes in modern astronomy. A 5 sigma detection, the gold standard of scientific certainty, directly contradicted by a clean null result. Subsequent observations producing signals that flickered on and off over days for no known physical reason. A community divided between those who insisted the planet was real and those who suspected the data had fooled everyone. This is the story of that discovery, that disappearance, and what both tell us about science at the very edge of what our instruments can perceive. The system nearest to us to understand why finding a planet around Alpha Centauri A matters so much. You have to understand what Alpha Centauri actually is. From the southern hemisphere on a clear night, it appears as one of the brightest stars in the sky. To the naked eye, it is entirely unremarkable, just another point of light in a sky full of them. But it carries a distinction no other star can claim. It is the closest stellar system to our own. Alpha Centauri is not a single star, but a trio, 3 gravitationally bound objects that have been locked together for nearly 5 billion years. The largest of them, Alpha Centauri A, is a yellow-white star remarkably similar to our own Sun, slightly more massive, slightly brighter, burning with the same steady warmth that astronomers associate with the best candidates for habitable solar systems. Its companion, Alpha Centauri B, is somewhat smaller and dimmer, about 85% of the Sun's mass, tracing a long elliptical path around its partner that takes roughly 80 years to complete. The two sweep as close as 11 times Earth's distance from the Sun at their nearest approach, and stretch out to 36 times that span at their farthest. The third member of the family is Proxima Centauri, a faint red dwarf barely a tenth of the Sun's mass, orbiting the A and B pair at an enormous distance. So far out that it takes nearly 500,000 years to complete a single orbit. Proxima is actually the closest of the 3 to Earth by a small margin, which explains its name. But for this story, it is Alpha Centauri A that matters most. It is sunlike, stable, long-lived, and familiar in exactly the ways that make astronomers imagine worlds around it that might not be entirely unlike our own. 4 light years. What that actually means. 4 light years sounds modest until you sit with what it actually represents. Light travels at 300,000 kilometers per second, fast enough to circle the entire Earth 7 times in a single second. And even at that speed, light from Alpha Centauri takes just over 4 years to arrive here. Every time you see that star in the night sky, you are seeing it as it was 4 years ago. The fastest spacecraft humanity has ever launched is Voyager 1, currently crawling through the outer edges of our solar system at roughly 17 kilometers per second. At that speed, the journey to Alpha Centauri would take approximately 75,000 years, longer than anatomically modern humans have existed as a species. And yet, by the standards of our galaxy, Alpha Centauri is essentially in our backyard. The Milky Way stretches 100,000 light-years across. Barnard's star, the second closest system to Earth, is already 6 light-years out, 50% farther than Alpha Centauri A. Every additional light-year compounds the difficulty of any future mission, adding decades or centuries to travel times. Alpha Centauri's proximity is not just an astronomical curiosity. It is a strategic geographic fact about our position in the cosmos. This is why Alpha Centauri has occupied the imaginations of astronomers and mission planners for decades. Projects like Breakthrough Starshot, proposed in 2016, have envisioned sending tiny laser-propelled spacecraft to Alpha Centauri at 20% of the speed of light. A journey of roughly 20 years, within a human lifetime. That is not science fiction. It is an engineering challenge of staggering difficulty, but an engineering challenge nonetheless. Before you can design that mission, however, you need to know what you are sending it to. The long hunt for a planet. For most of the 20th century, astronomers had no way to determine whether Alpha Centauri had planets. Planet detection technology simply did not exist. Stars were points of light, and any planets that might orbit them were invisible. Too small, too dim, too completely overwhelmed by their parent stars. It wasn't until the 1990s that astronomers began finding planets around other stars at all. Those early discoveries relied on indirect methods. The radial velocity technique detects the tiny gravitational wobble a planet induces in its host star. Both the planet and the star orbit their shared center of mass, causing the star to shift back and forth slightly, a motion detectable as a tiny stretching and compression of its light spectrum. The transit method monitors a star's brightness over time and watches for the characteristic dips that occur when a planet passes in front of it, blocking a small fraction of its light. Missions like Kepler and TESS use this approach to catalog thousands of planets around distant stars. Both methods transformed our understanding of the universe. We went from knowing 9 planets in our solar system to cataloging more than 5,000 confirmed worlds orbiting other stars. We now know that planets are not rare. They are the rule. Most stars have them. But neither technique works well for Alpha Centauri. The transit method requires geometric luck. The planet's orbit has to be aligned nearly edge-on to our line of sight, and the probability of that alignment is only a few percent. The radial velocity method faces a different obstacle. Alpha Centauri is a binary system, and the mutual orbital motion of its 2 stars creates a large background signal that makes buried planetary wobbles extraordinarily difficult to extract. Several claimed planet detections around Alpha Centauri B were announced over the years, and later retracted when more careful analysis revealed the signals were data artifacts rather than genuine planets. This left a third path: direct imaging. The fearfully next to a lighthouse direct imaging is the most intuitive method for finding planets, and the most brutally difficult. The problem has 2 parts. First, planets are extraordinarily faint. They produce no light of their own, shining only by reflecting starlight or radiating residual heat from their formation. Jupiter reflects sunlight about 1 billion times fainter than the Sun itself. Seen from Alpha Centauri's distance, it would be essentially invisible. Second, from our perspective, planets appear physically very close to their stars in the sky. Even at Jupiter's distance from the Sun, seen from 4 light-years away, it would appear separated from the Sun by only a few arcseconds, an angle so small that the scattered light from the star spills across the planet's position and buries any signal it produces. The tool that makes direct imaging possible is a coronagraph, a precisely shaped mask that blocks a star's disk and reveals whatever faint companions might be nearby. The concept mimics what happens during a solar eclipse, when the moon blocks the sun's disk and the faint outer corona blazes into view. Ground-based coronagraphs face a major additional obstacle: Earth's turbulent atmosphere, which blurs stellar images and creates a halo of scattered light that buries any nearby companion. Adaptive optics systems can partially correct for this, but cannot eliminate it. Space removes the obstacle entirely. Above the atmosphere, stars are points of light as sharp as physics allows, and a coronagraph can block a star's disk with far greater precision. The James Webb Space Telescope, launched on Christmas Day 2021, took this capability to an entirely new level. Its primary mirror stretches 5 meters across, nearly 3 times Hubble's diameter, and operates in infrared wavelengths where planets emit their own heat rather than merely reflecting starlight. A young or massive gas giant, still warm from its formation, radiates at infrared brightness levels, dramatically easier to detect than reflected visible light. Webb's instruments are cooled to below -230 degrees Celsius to prevent the telescope itself from glowing in the infrared and swamping the faint signals it is trying to catch. The combination, large mirror, infrared sensitivity, cold operation, space-based coronagraph, made Webb the most capable planet-hunting instrument ever built. And Alpha Centauri A sat near the top of its target list for one additional reason. Because the system is so close to us, any planets orbiting it appear at larger angular separations from their star than planets around more distant systems would. That larger separation makes them easier to place on a coronagraph mask and easier to separate from residual scattered starlight. In early 2025, a team of astronomers proposed using Webb to search for planets around Alpha Centauri A. The proposal was approved. In the spring of that year, humanity pointed its most powerful eye at its nearest stellar neighbor and waited to see what the darkness around it held. The discovery. The observations ran over several weeks, with Webb locking its gaze on Alpha Centauri A with extraordinary precision, holding the star centered on its coronagraph mask to within a fraction of an arcsecond for hours at a time. Each session recorded millions of photons, most from residual starlight that scattered around the mask's edges or reflected off microscopic mirror imperfections. The star was blocked but not silenced. Its glow spread across the detector like fog around a street lamp. To separate real objects from instrumental ghosts, the team used roll subtraction, rotating the telescope between exposures so that artifacts tied to the instrument appear at different positions in successive images, while a real planet fixed in space stays put. They also observed across multiple infrared wavelengths, looking for the characteristic spectral signatures of gas giant atmospheres, specific patterns of absorption at wavelengths associated with methane and water vapor, the molecules expected in the upper layers of warm gas giants. Then, in the processed data, something appeared. A faint point of light emerged from the noise at a position roughly 2.7 astronomical units from Alpha Centauri A, approximately the distance of the asteroid belt in our solar system. It appeared in multiple independent images at different times and different telescope orientations. It did not rotate with the telescope when the roll angle changed, confirming it was not an instrumental artifact. It did not appear in any archival star catalog or previous sky survey. Its spectral properties matched a warm gas giant, consistent with a planet roughly the mass of Saturn, still radiating residual formation heat at a temperature somewhere between 500 and 1000 degrees Kelvin. The statistical confidence of the detection reached 5 sigma. In the language of particle physics, the field with the most rigorous standards for claiming a discovery, 5 sigma is the threshold for announcing something real. At 5 sigma, the probability that the signal arose from pure statistical noise is less than 1 in a million. The team reviewed their work independently, cross-checked calibrations against other datasets, and consulted outside colleagues. Everything held. In August 2025, they submitted their paper to a peer-reviewed journal and simultaneously released it publicly through a preprint server. The announcement reached the world within hours. Planet found orbiting Alpha Centauri A, science outlets, News organizations and social media carried the story everywhere. The public response was immediate and emotional. Not just excitement, but something closer to awe. A sense that the universe had become slightly smaller, slightly more knowable. Alpha Centauri had always been the nearest star. Now it might be the nearest solar system. Mission planners began updating calculations. Breakthrough Starshot suddenly had a more compelling destination. The system was no longer a target of hopeful speculation, but a place with known architecture. A solar system beginning to take shape before human eyes. The planet vanishes, then October arrived, and the planet was gone. A second independent team pointed Webb at Alpha Centauri A, using the same instruments, the same coronagraph setup, the same observing techniques. Their purpose was straightforward: observe the planet at a different point in its orbit and begin the confirmation process that all major discoveries require. They had every reason to expect they would see what the first team had seen. The star was there. The planet was not, where the infrared point of light had appeared. 2 months earlier, there was nothing. No faint glow at the expected position, no trace of warmth anywhere nearby. The field around Alpha Centauri A was clean and empty. The team ran their data through every available analysis procedure. Nothing. They published their non-detection in November 2025. Careful in their language, precise in their conclusions, not accusing the original team of error, but reporting with the same rigor what the data did not show. The reaction from the astronomical community was immediate. The central question was one nobody could answer cleanly. How does a Saturn-mass planet disappear? On first principles, it cannot. A Saturn-mass object contains roughly 95 times the mass of Earth, compressed and held together by gravity. That mass does not evaporate. It does not switch off. The only process that could destroy such an object would be a catastrophic collision with another massive body. And even then, the result would not be silence. It would be a superheated cloud of debris radiating intensely in infrared, easily detectable by Webb for years. No such cloud appeared. Alpha Centauri A in October looked exactly as it always had. A quiet, middle-aged star with no sign of recent catastrophe. Possible explanations, none of them satisfying. The astronomical community worked through the available explanations. The first was a false positive. The original signal was not a planet at all, but some instrumental artifact or background contamination that fooled the first team's analysis. False positives are a real problem in direct imaging, where faint signals must be extracted near overwhelmingly bright stars. Several confident planet announcements in the past were later retracted when more careful analysis exposed systematic errors. The original team pushed back firmly. Their detection had reached 5 sigma, survived roll subtraction, matched no archival catalog entry, and carried the spectral fingerprint of a planet. 5 sigma false positives from pure statistical noise happen less than once in a million trials. If the signal was false, something systematic had fooled them, and they could identify no such effect. The second explanation was occultation. Perhaps the planet was real but had moved directly behind the star, hidden not because it had disappeared, but because Alpha Centauri A itself was blocking our view. This happens in our own solar system. Venus passes behind the Sun roughly every 19 months, temporarily invisible. The math, however, did not cooperate. At 2.7 astronomical units, the planet would travel only about 20 degrees along its orbit in the 2 months between observations. For that motion to carry it directly behind the star, the orbit would have to be oriented almost perfectly edge-on to our line of sight, a geometric alignment with a probability of only a few percent. The third explanation was catastrophic destruction. What if a massive collision had destroyed the planet in the brief interval between observations? Planetary collisions are not impossible. Our moon likely formed in one. But Alpha Centauri A is 5 billion years old. Any planetary system it hosts has had billions of years to settle into stable orbits. Dynamical models predict that major planet-planet collisions in mature systems are extraordinarily rare, perhaps once per billion years per system. The probability of one occurring in any specific 2-month window is roughly 1 in 6 billion, and even if one had occurred, the result would be a brilliant expanding debris cloud, not the complete silence the October observation recorded. What remained was a set of explanations that were individually improbable and collectively unsatisfying. The flickering more observations followed in December 2025. The Webb Time Allocation Committee took the unusual step of approving multiple programs simultaneously, reflecting both the urgency of the question and the fact that no satisfying resolution had been found. Multiple teams observed across different infrared wavelengths with different instruments. The strategy was comprehensive. If the planet was there but had somehow changed, multi-wavelength coverage might reveal what had shifted. What came back was stranger than silence. In some December images, a faint point of light appeared near the position of the original detection, significantly dimmer than the August signal, barely above the noise threshold. But there, appearing in multiple independent images from the same observing session. Its spectral properties were broadly, if weakly, consistent with a planetary source, but it was consistently visible. In other images from the same observing run, taken just hours or days apart, the signal vanished. One session would record a faint hint of something, the very next would record nothing. Different teams analyzing the same raw data reached contradictory conclusions. Some argued the faint signals were real, at the correct position, with consistent spectral behavior. Others argued they were noise, random fluctuations near the expected location too marginal to trust. January's observations compounded the confusion. One session detected a source at roughly 30% of the original August brightness. Another session, 3 days later, showed nothing, with an upper limit indicating any source had to be fainter than 10% of the August signal. A third session a week after that showed something again, even fainter, and at a position slightly offset from where the planet's predicted orbit placed it. No known physical object behaves this way. Planets are stable sources of light. Their brightness varies slightly as they rotate. Different cloud patterns coming in and out of view, but those variations are small, typically a few percent, and predictable. They do not flicker on and off by factors of 3 or 10 over the course of days. They do not appear in one observation and vanish in the next. Stars vary, but in characteristic ways. Regular pulsations, predictable eclipse patterns, fast flaring events. None of these signatures matched what the Alpha Centauri data was showing. The flickering had no period, no regularity, no recognizable pattern from any known class of astronomical object. This forced a harder question onto the table. If the original planet was real and genuinely varying in brightness by these amounts on these timescales, something physically unprecedented was happening in its atmosphere. Gas giant atmospheres are dynamic. Jupiter's Great Red Spot has been shrinking for decades. Saturn produces planet-encircling storms every 30 years. Neptune lost an entire massive storm system between the Voyager flyby and Hubble's first look a few years later. But none of these changes cause a planet to disappear from view entirely and reappear days later. Jupiter's brightness varies by perhaps 10 or 20% over years. For a planet to drop from detectable to completely undetectable and back again in 72 hours would require atmospheric changes of a speed and magnitude never observed on any world we have ever studied. A phenomenon with no analog in all of planetary science. One possibility raised was an extreme haze event, a sudden thickening of high-altitude aerosols temporarily blocking the planet's infrared emission. Gas giant atmospheres do contain haze layers built from organic molecules created by ultraviolet photochemistry. But producing a change large enough to render the planet invisible and doing so in days rather than years pushed well beyond what any existing atmospheric model could accommodate. The Galmunity Divides. By February 2026, the astronomy community was thoroughly divided. One camp argued the original detection had to be a false positive. The flickering seen in December and January was, they argued, simply the noise floor of Webb's instruments being misread as signal by teams predisposed to find confirmation. Extraordinary claims require extraordinary evidence, and a planet that appears and disappears is not behaving like any planet in the known universe. The simpler explanation, they concluded, was that it was never there. The other camp argued precisely the opposite, that the flickering was itself the discovery, that something genuinely unusual occupied that location in the Alpha Centauri system, something outside existing categories, and that the inconsistent detections were pointing at an unknown physical phenomenon rather than at analytical error. Both positions were defensible. Neither could be proven with the available data. The universe was offering no easy resolution. What history teaches US science has been in situations like this before. In the 1840s, anomalies in Mercury's orbit led astronomers to propose a planet called Vulcan, orbiting closer to the Sun than Mercury. Several reputable observers claimed to have seen it. Searches continued for decades, sometimes producing apparent detections, sometimes finding nothing. The debate persisted until Einstein's general theory of relativity explained Mercury's orbital behavior without requiring any additional planet. Vulcan had never existed. The claimed detections had been misidentified stars and wishful thinking, sustained by the very human tendency to find what you are already looking for. In 1996, a NASA team announced that a Martian meteorite recovered from Antarctica contained microscopic structures that might be fossilized evidence of ancient life. The announcement made headlines worldwide. Nearly 30 years later, it remains scientifically unresolved. Alternative non-biological explanations have been proposed for every feature the original team identified. The question simply stays open, sustained by ambiguous evidence that neither side can definitively interpret. The Alpha Centauri planet may follow either of these arcs. It may eventually be confirmed. More observations accumulating, the flickering explained, the detection becoming stable and consistent across multiple teams. Or it may be retracted, deeper analysis revealing a systematic error, the faint December and January signals recognized as noise, the episode filed away as a cautionary lesson in the difficulty of direct imaging. Or it may do what the Martian meteorite has done, simply persist unresolved. A marginal detection sustained by ambiguous data while better instruments are developed and better observations are planned. What this episode already teaches us. Whatever the ultimate outcome, the Alpha Centauri planet episode has already taught the field several important things. It has demonstrated that direct imaging of exoplanets, even with the most capable space telescope ever built, remains right at the edge of what is technically possible. Webb was designed for this kind of science and performs extraordinary science. But extraordinary is not infallible. When you operate at the noise floor of your instruments, searching for signals barely above the threshold of detection, small differences in observing conditions, calibration choices, and analysis methods can determine whether a source appears or disappears in the final image. Marginal detections require heightened scrutiny precisely because they are marginal. It has also demonstrated that the astronomical community's self-correction mechanisms work as they are supposed to. A major claim was made with strong statistical support. It was immediately subjected to independent verification. When that verification failed, the non-result was published with the same transparency as the original announcement. No one suppressed the contradictory evidence. No one waited in silence, hoping the controversy would quietly go away. The back and forth played out in public in real time, exactly as the scientific process is designed to function. That is not a failure. That is the system working. What has changed from previous generations is the speed and visibility of that process. 50 years ago, a discovery like this would have appeared in a journal article, read by a few thousand specialists. The follow-up non-detection would have been discussed at conferences and gradually absorbed over years. The public would never have heard about the controversy at all. Today, preprint servers make results available within hours. Social media carries them to millions of people before formal peer review is complete, the full arc. Discovery, doubt, debate unfolds in public view with all its messiness exposed. This transparency has genuine value. It allows people to see how knowledge actually gets made, rather than receiving only the sanitized final version, in which everything was discovered cleanly and confidently. The lesson, when preliminary results are later questioned, is not that scientists are unreliable. The lesson is that science at the frontiers looks like this: provisional, contested, self-correcting, and that is a feature, not a flaw. The Search Continues the episode has concentrated an extraordinary amount of scientific attention and resources on Alpha Centauri. Dozens of research groups are now planning or conducting observations with instruments beyond Webb. Ground-based telescopes equipped with adaptive optics are being trained on the system regularly. The extremely large telescope, nearing completion in the Atacama Desert of northern Chile, with its 39-meter primary mirror, will be capable of staring at Alpha Centauri A on every clear night, accumulating data at a rate no space telescope with limited scheduled time can match. NASA's Habitable Worlds Observatory, currently in early development, is being designed with nearby sun-like stars as primary targets, and Alpha Centauri A is at the top of that list. Within the next decade, we will almost certainly know whether Alpha Centauri A has planets. Not because of one observation or two or three, but because the accumulated weight of evidence from multiple instruments using multiple independent methods will eventually resolve what any single observation cannot. That is how science works at its best, not in sudden flashes of revelation, but in the patient buildup of evidence until the picture becomes undeniable. What this really means: Alpha Centauri sits in the southern sky. Visible on clear nights from Australia, South Africa, and South America as one of the brightest points of light above the horizon. To the naked eye, it is completely unremarkable, indistinguishable from dozens of other bright stars, giving no indication that it holds any special significance. But it is not ordinary. It is the nearest sun-like star to our sun. It is the first place beyond our solar system that humanity might realistically send a probe within the span of a few lifetimes. And somewhere in the darkness around it, in the space between its light and ours, there may be worlds, warm, orbiting, real. We do not yet know if those worlds exist. The question that seemed briefly answered in August 2025 is still open. The data is still contested. The community is still divided. The universe is still withholding its final answer. But we are looking. For the first time in human history, we have instruments capable of genuinely searching for planets around the nearest star. We have methods sophisticated enough to detect the faint infrared warmth of a world 4 light-years away. We have the will to point our best technology at our most important nearby target and ask the question directly, not through analogy or statistical inference, but through actual observation. The only things standing between us and a definitive answer are time, careful observation, and the slow accumulation of certainty that science demands before it will say, yes, this is real, this is there, this is a world. That answer is coming, and when it arrives, it will be one of the most significant things our species has ever learned. End.